Close. Hi, everyone. Welcome to PyData NYC. Hope you're enjoying the food. Let's give everyone a moment to find a seat and settle down. Plenty of room in the front, by the way. So for those, how many of you are here for the first time? A lot of you. Okay, so what is PyData? PyData is the educational program of NumFocus. And NumFocus is the nonprofit that supports a lot of the Python scientific software that we all use. So if you ever use NumPy, Pandas, scikit-learn, stuff like that, all sponsored by NumFocus. And we also have code of conduct. If you don't know what it is, scan that, read it. In short, PyData is committed to providing a friendly, safe, and welcoming environment for all attendees, regardless of gender, sexual orientation, disability, ethnicity, or any other personal characteristic. And these are our organizers. I'm up there somewhere over there. And
cool. I guess if you're interested in volunteering.
If you're interested in volunteering, please reach out to one of us. I'm AJ, this is Abby, and there's some more of us scattered in the audience.
Nikhil, right there.
Yeah, raise your hand higher so they can see you.
And then Steve is down at the first floor, as well as Cryptomoy. But yeah.
And we want to say thanks to our sponsor, Microsoft. They have provided food and drink and the space for us to have these events. Next up is.
Should I stay
Next up is Shafik, and he is an engineer with the New York Times. And he has a background in computer vision research and has worked on several applications of computer vision and ML over the course of his career in both government and the media space. So everyone put it up for Shafik. Multi-Modal Machine Learning and image visualization and segmentation.
Yes.
So would Shafik prefer if we ask questions after this talk, or would you also mind that we ask questions during it as well?
After, because we have networking after, so it can roll in. Yeah. Sorry, can you share your screen for the recording?
Yep.
Part of the, oh yeah, probably on that one.
Share. Okay. Oh, I have to do the system preferences thing.
Yeah,
okay.
That's the tricky thing about it.
All right. You can all see my password. Nice.
No, just take it off. Yeah,
Okay.
just take it off.
Hold on.
Does anyone here not have a raffle ticket? I can show you the raffle prize if you need time. We have machine learning solutions architect handbook. We have building LLM powered applications, and let's see, transformers for NLP and computer vision, and PyTorch. Torch is very nice. We actually had the co-founder of PyTorch at our last conference as a keynote speaker. He gave a really cool talk about, and it was full of cats. So that's all I remember. Oh, okay. AJ or Nikhil. Nikhil can unmute. Nikhil's back there. Yeah.
Should I share?
Yeah, that one should be fine. And then you can turn on your camera if you'd like. Do you have a camera?
Yeah.
Or I can turn on my camera and you can just present like this. There you go. That's fine. Yeah. Totally
okay.
fine.
All right. That's good, I guess. I've never used this WebEx thing.
I know WebEx is not fun.
Okay.
We are switching to Microsoft Teams.
Nice. Okay. Okay. I think. All right. Yeah,
It's sharing your other screen right now.
it's sharing my other
Oh,
screen.
okay, yeah, okay, no, you're good.
Okay, cool.
Okay, here you go. You just have to plug in your
Yeah, gotcha.
thing.
Cool.
Sorry, I can't do it.
No problem.
Wait, can you do
Yeah, I
it?
got it. All right.
Yeah, here you go.
Okay.
All right, we'll give it a couple seconds. It won't show, so.
Okay, gotcha. Okay,
Yeah.
great. Cool. Thanks for coming to my talk. I'm happy to present here this meetup. I did meetup today. So just there was a brief introduction to myself, and I'll be talking about multimodal machine learning. I've talked about this at quite a few places before, well, 3, I think, to be specific, and I've given some variants of this presentation at those places. Just a little precursor that this is a little bit, it's a deeper presentation on the technicals, but I think that should be fine. I'm not going to linger too long on anything too specific, so just to give you a heads up to clear your heads. Okay, so the outline of the talk, I'm going to have well, I'll just ask the question now. At this point in time, how many people are familiar with multimodal models right now? Okay, cool. That number increases every time that I give this talk. That's good. And if not, I'll go over it in the next slide. I'll be also talking about multimodal perception for a very short period, just to motivate some interesting discussion. I'll be talking about multimodal machine learning, and that's like the crux of this talk, along with examples and demos and things like that. And also be, again, the demos, frameworks, and other things that people have put together over the years to do multimodal learning and just applications more effectively. So just briefly, for those who didn't raise their hands, which I think most of y'all, but still, I'll mention it. When I say multimodal, a modality, the modal, refers to a specific type of input data such as text, image, audio, each providing different informational content that can be integrated to enhance model performance. So basically, if you use GPT or any other model where you can upload some PDF or you can upload images and then type some text and get some enhanced representation of an output, right? That would be a multimodal system because you're using different kinds of data to produce that output. And so specifically, this particular example, and referencing the work that I mostly worked on a while ago, was matching ultrasonic signals, ultrasonic microdoppler signals to be specific, and seismic signals together to enhance personnel detection. And this was done through the context of sensor fusion. So the sensor output on the left is what's called ultrasonic microdoppler. Not sure how many people are familiar with how Doppler works, but essentially when you're walking or something is moving, there's disturbances to media, spatial media, the air, and in that disturbance, that's essentially an audio disturbance. As a person moves or as something moves and rotates and vibrates in the environment, they give off acoustic signals that are not audible. They're in the ultrasonic domain. And so you can have a sensor which picks these up. And that sensor is actually really good for a lot of things, specifically moving individual arms, legs, etc. And you can use that data to help identify who a walker might be, or a moving object might be, a dog, a cat, a person, how tall they are approximately. The problem with that is that that sensor falls off over time because it's actually very susceptible to high frequency degradation. So you have to combine that sensor information with seismic sensor data, which is the person walking across some terrain will emit signals in the forms of S waves and P waves that will vibrate the ground, and those will produce some sort of waveform which characterizes the person's cadence and their characteristics and other things about the person. That sensor is great and has limitations of its own. But when you combine both sensors through multimodal fusion, then you have a much better sensor estimate and a sensor output of a moving person or something. in the environment. So that's just a little bit of motivation. So I'm gonna like play some videos to this. A lot of these are like interesting, not my own, but this is something called the McGurk effect for anybody who's familiar.
It's called the McGurk effect. Ba, 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 ba. What do you think he's saying? If you think he's saying da, 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 you are in the grand majority. But now, close your eyes and listen instead of watching. Ba, 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 ba. The voice is saying ba, ba, ba. Now, let's replay it without the sound. Yes, it's true. His lips are saying ga, ga, ga. So how is it that when the lips are saying ga, 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 and the sound says ba, 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 that our brains read da, da, da? The McGurk effect. It's an example of an auditory illusion. It's a great way to show that the accurate perception of information can involve the participation of more than one sensory system. In this case, vision with sound. We call it multimodal perception. The McGurk effect. It's a terrific example of the fact that the senses did not evolve in isolation from each other, but actually work together to help us perceive our world. When multiple senses are stimulated simultaneously, the brain begins to experience an information-rich learning experience and laps it up like ice cream. It encodes more information per unit time, and it remembers that information better too.
Cool. So that's, again, a pretty common example and popular example of demonstrating multimodal perception in the human brain. I'll get to the machine learning part in a bit, but just to kind of give you more of what's going on there, like the canonical example is that if you have a sonic event, an auditory event, and a light-based event that occur pretty far in time, separated from each other, then you'll have a clear separation of event in the human brain. So for example, if you have a drum beating and you see the drum beating the skin, but you don't hear the beat for a long time, you'll perceive those as two separate events, like somebody beat a drum somewhere else. But just visual perception was a different drum beat. So if the events are very close together, for example, if somebody beats the drum and right away you hear the sound, you have the fusion, automatic fusion. So there's actually not too much learning going on because your brain automatically perceives those as two similar events. And now these are simplified cases too, but this is just for the purpose of the illustration. And then the most challenging part, or most challenging perceptual manifestation is if you have the events close in time together. For example, a drum beats, you see the drum beat, and then later you hear the drum beat slightly off time, but enough that your brain is not sure whether the drum beat was the same event or not. Then your brain will proceed with its experience, and it's already understood learning, and it will try to create some sort of best estimate based on a lot of factors underneath the hood. So that's enough of the human brain. Let's talk about the machine models. So this is going to be familiar to people who already understand machine learning to some level, but there are different modalities of data. Text is a modality, sound is a modality, vision is a modality. You have different unimodal architectures which are good at learning on those data types. For text, you have the state of the art is the transformer models, right? So everybody knows what those are, I guess. GPT is an example. And LSTMs are also an example from a long time ago. For images, you have CNNs, convolutional neural nets, and they're good at extracting spatial hierarchies from images and automatically learning features from the most minute patterns in an image, and then doing learning to characterize what is going on in that image and classifying it. And those also, vision transformers are another type of architecture that's good for that. And then for audio, you have recurrent neural networks for anything that's temporal sequences. And those are specialized in things that have 1, 2, 3, 4, I think that there's some sort of tie-in between an event in the past and in the future. And you can combine those with, for example, CNNs, and then you can analyze spectrographic patterns. I'll talk about the Whisper model later, which does some of that under the hood. So moving on. Okay, so the whole idea when you computationally frame this is that you're looking at something called cross-modal interactions. Essentially, vision, audio, all the modalities, they interact in some manner. When we talk about interaction, we're talking about informational interaction. Okay, so they're providing simultaneously information about a particular phenomenon. And a lot of the times this information is complementary, right? So you have information like you see something happening in the environment, right? And you just use your sight. That will give you some picture of what's going on. But then there could be sounds in the environment, like for example, birds chirping or something that lets you know that birds are there without necessarily seeing them. So that's complementary information that both modalities provide. And then understanding these interactions and knowing how to combine them allow for things like multimodal sentiment analysis. So what that is that if you take an image, and people who's familiar with sentiment analysis here, I'd imagine the great majority. So when you're looking at text, the text is either positive, negative, neutral, or political, not political. There's different kinds of sentiment and sentiment-like scores. Images too can also provide that as well. For example, image of a dark forest can give you a sentiment of a negative sentiment maybe, as opposed to a very brightly lit forest. So that allows for visual question answering, like what's going on in this video. This is something that's like a huge area of research right now in many of the companies that are producing AI products. And that's really where things are really going to, like, okay, is there a fire in this building? There's smoke rising out of it? What's going on? As the video moves on, then more questions can be asked about the image data and whatnot. And then HCI, human-computer interaction systems. So those are things like assistive devices to help a person interact with their environment, maybe use a phone to help them, like they can use it if they're disabled, they can use their eyes to control the different apps on the phone, like through image recognition. That's a modality. And then auto image captioning, which is a very common thing that most systems these days have. So putting like some kind of caption on those images. So I'm just going to play another video for who watched I/O. Anyone? Google I/O. Okay, so you probably know what this is.
Okay, let's do some tests. Tell me when you see something that makes sound.
I see a speaker, which makes sound.
What is that part of the speaker called?
That is the tweeter. It produces high-frequency sounds.
Give me a creative alliteration about these.
Creative crayons color cheerfully. They certainly craft colorful creations.
What does that part of the code do?
This code defines encryption and decryption functions. It seems to use AESCBC encryption to encode and decode data based on a key and an initialization vector, IV.
That's right. What neighborhood do you think I'm in?
This appears to be the King's Cross area of London. It is known for its railway station and transportation connections.
Do you remember where you saw my glasses?
Yes, I do. Your glasses were on the desk near a red apple.
What can I add here to make this system faster?
Adding a cache between the server and database could improve speed.
What does this remind you of?
Schrodinger's cat.
All right, give me a band name for this duo.
Golden Stripes.
Nice. Thanks, Gemini.
So, yeah, Google got a lot of clapping for that one, so. But those things are becoming more common now these days, multimodal assistants and whatnot. So the future is here in that regard. So let's talk about, go back to OpenAI now. Let's talk about Clip. So anybody familiar with Clip? Okay, great. Clip stands for Contrasted Language Image Pre-training, open source multimodal AI model that understands and connects visual concepts with text descriptions. So under the hood, these kinds of models are really powering, and Clip came out in 2021, but it's still powerful and still does a lot of things. And these kinds of models are powering the multimodal landscape. The model is trained using a vast data set of images, text pairs, and visual concepts from a variety of internet source images and associated descriptions. I don't think it was ever told how many images exactly Clip was trained on, but it was quite a bit, a huge amount. And it can be applied to a very diverse set of applications, and it can do things like zero-shot or few-shot learning, which means it can learn from things that it's never seen anything like before, because it uses both text and multimodal understanding to pick out something, which is actually almost kind of like black magic, but it's what it is, what it does. So this is a demo that I put together. Now here comes my demos, the things that I'm putting together. A lot of them are in Python. This is PyData, so it should be appropriate. Okay, so I'm going to go over a quick demo of Clip. Clip is the OpenAI framework, open sourced framework for doing visual object detection. That's pretty popular. It's based on the Vision transformer. And the simple example that I have here is just taking an image of a cat. So I have this image of a cat here. And then, so basically what we do, we set up our Clip model, and then we set up our Clip processor. So I have this all coded up here to do this. And we pretty much run the processors in order to make sure we condition the input to be ingested by the Clip model. And then I have image captions here, which I have listed as cat, dog, mouse, horse, boat as categories of image captioning that the Clip model will detect as a percentage of being input represented in a specific class. So I'm going to run this real quickly. And what should happen is Clip should run and give us an output that shows that we are a certain percentage of cat, dog, etc. And so the output is 96.91% cat, 1% mouse, 1% dog, 0% boat, essentially 0% boat and horse. So now let's use different captions for Clip. So again, if we use the ImageNet captions, because Clip has been trained against millions and millions of data points. So I'm going to give a wider variety of different classes. And if I run this, as you can see, Clip now runs, and it now has a harder time determining what specific cat it is, but thinks it's mostly a Madagascar cat. So one thing that's really cool about Clip, it has demonstrated the ability to do zero-shot learning. So it can learn on things that it's never seen before, but more models in the future have gotten better at this and better over time. Okay, thank you. Cool. So back to slideshow. Okay. Okay, so basically that's the foundation of things like multimodal search systems. Okay, so this is an example of like a kind of like a high-level schematic for like what a multimodal search-based system would be. So if somebody's, for example, queries for something like wild animal, right? On the bottom you have a semantic layer, which does like this text embeddings and whatnot, and it will classify and produce things and outputs that are like wild animals, okay? And so let's say in this system you have a secondary level of searching occurring, or a secondary level of output where you have something like bears, or you have bears, cows, dogs, etc. And then a person may click on the bear and then get a further characterization of what might be a wild animal. In that case, it will use a convnet to like break down the images there and like do the hierarchical learning and classification against its learned architecture, its learned structure. And then what would happen, what's the difference here is that in multimodal systems with cross-modal embeddings, you have this idea of correlational loss. And so the loss functions in traditional machine learning systems that most people are familiar with are things like mean square error, mean square loss, mean absolute error, and those are loss functions against one data stream, so to speak. In this case, you're trying to find the most correlated data between two different multiple output data streams that are simultaneously being linked together. And that's essentially what you're trying to map. You're trying to maximize the correlation by minimizing the correlational loss. I'll get into that in a bit. So then that leads to things like visual image search. So you can match, we did that already, match the text descriptions with relevant images. And so it's very good in visual image search in general, right? So in Colab, I created like a simple visual image search system using Clip. And so without, there's no voice in this, so I'll just describe what's going on. I have the same kind of setup. And I also enhanced this with another framework called Detectron 2. That's a meta framework, but I won't go too deep into that. So basically, if I put in the word cat, I initially put in the word dog and it found a dog. Then I put the word cat in, and this is not doing like label lookup. This is actually doing the learning to find from my folder of different images, cats. So it's picking out cat.png, but other things like image.png, there's no meta that indicates that this is a cat. It'll just do this quick image search and it'll just go through and find another cat. So there's all the cats in my folder. I have a folder of different images. And then finally, if I go through this, just skipping towards the end, I have an image of a cow and I asked it to find the cow. And so it's not perfect, right? Because it thinks this image is 77% cow, but it also thinks there's a person in here too. Like this part looks like a person to the image. So again, there's like, aberrations and things you have to refine with the models, but that can be done. And so that's like something with visual image search. Another usage of Clip, now this is a personal project that well, I'll go into that in a bit, but this is, everyone familiar with style transfer at this point, right? Okay, cool. So style transfer, and I'll just play it while it's going, is just basically where you have a style of a particular image, and it can be extracted. The style is represented in a very specific manner. It can be extracted from the image and then applied to another image. So for example, this is Stable Diffusion, and then I'm just asking Stable Diffusion to generate a car in the style of Van Gogh. The AIs that are used are trained to recognize style and separate that. And that's a whole, I do a whole talk on the specifics of that, so I'm not going to get too that deep into that, but that has its own interesting implications. And so these are great for designers who want to replicate patterns, and it's used, I guess, in the fashion industry and all over the place now to kind of like create something in the style of something else to make it easier without having to do prototyping as much. But then the question with that is that if you can do that, then you can steal people's styles very easily and without paying them. And that's the whole crux of the thing that I'm interested in there. So just quickly what neural style transfer looks like. I'll get back to why this is important to Clip in a second. Okay, and now this should do it. So basically, I have an image here. Okay, now you see, I'll mute myself for a second. I have this image of this person here, and then I have this style image here. This is just a random image, and then using style transfer, you can combine those two, and you get this stylized person. All again in Colab, so it's kind of interesting. And then you can do that with any image and extract a certain percentage of its quote style and apply it to the image again, and the image becomes stylized. So, and you can do this with a video too. Left. So this is basically a video of me talking, right? Like I'm just saying a bunch of things or whatever. I take that image, I do frame by frame replication, and then I can style my video very easily. And you can control also the style outputs. So where Clip comes back into play is that we use something called, now this is a system that I'm working on with some compatriots of mine. So You can match the style of images to content for known artists. And clip is one way you can help create sort of an attribution score to help determine whose style is being replicated for a particular image. This is a very rough demo. This is a long work in progress. It's a lot of actually fundamental research that I'm working on, so I'm not getting too deep into that now. But basically, if I search for like image, this is, like for example, I search for an image of a Monet image. I search for Starry Night. It'll pick up, oh, that this is a Van Gogh with an 85% image. And then you can do this like, the idea would be to like try to do it for more complicated cases where the artist isn't as well known. There's some ethical implications in all of that too, but what happened to my thing? Okay, cool. So let me, what's going on here? Oh, sorry. Okay. Okay, so fusion techniques. Okay, how much time? Okay. So basically, everyone's familiar with embeddings now at this point. You've all got to be. Okay, so embeddings are just, it's essentially the representation of data that is in the latent space of a particular model. It's you can call it the kind of the machine understanding of something, right? So I'm just kind of simplifying it for like not overly like heavy, complicated stuff going on, but again, they're represented as dense vectors, and they're more like efficient, lower representations used for machine learning tasks. Now, those are, you might know unimodal embeddings, but there's something called cross-modal embeddings, and that's when you have multiple modalities have their embeddings all crammed into the same representational space, which would be called a multimodal embedding space. And multimodal machine learning models are specifically designed, certain ones, to semantically align this data in the cross-modal multimodal embedding space. I'll get to those in the next slides. And then once you do that, because you have multiple modalities combining their data into a similar space, you run into the curse of dimensionality, which means you have a lot more data and you have to do dimensionality reduction to make sure that the space is manageable. Otherwise, your models get humongous. So examples are like TISNE or PCA, you've heard of those. But like then for multimodal cases, there's specific ones like called canonical correlational analysis, a few other kinds. And so what happens here is this is a quick slide on like how the fusion itself works, right? The fusion itself is its own different thing besides the multimodal learning. So for instance, if I have multiple, now this is two different ways of fusing the data. You have something called early fusion, and then you have something called late fusion. Early fusion is basically when you take all of your features and then you put them together very early in your fusion process, and then you do classification on them or machine learning on them. That's what this SVM is here, support vector machine example. Late fusion is when you do machine learning in all of your inputs, and all of these are just different text features, right? Like these are all bad words, 2 grams, n grams, LDA, WordNet, etc. And you run a machine learning classifier unimodally each on each of these features, and then you output, you do your fusion after all of that's done. So early fusion, there's trade-offs there, and there's things called middle fusion, hybrid fusion, etc. The early fusion situation is good when you need to make sure you get the most rich representation of your output data and want to do the most complex learning, you'll try to do it earlier. Late fusion is when you do things, you want to avoid a lot of the complexity of the individual modalities, and you just want to get the final output. And late fusion, it usually leads to less data, and again, the trade-off is really that late fusion is great for when you are like, if your individual modalities are noisy in their own landscapes, and you just need to do something to extract the most correlated efficient representation. That's where you get late fusion models, but late fusion loses a lot of information. Early fusion gives you a lot of information, but it gives you too much information. So ultimately, you have to figure out which one to do and which situation. I'm going to skip over a few things, but the reason I'm talking about autoencoders is because a lot of the models that are used for used for fusion are using the encoder-decoder architecture. And so if the basic autoencoder setup is that you take an image or something, you take some kind of input, you compress it into some latent space, and then you just decompress it, and you get the same thing out with small variations. So it's probably the simplest neural network type that doesn't just do plain classification. And there's different types of autoencoders out there, and they're useful for different things like anomaly detection and pre-training other neural networks for different tasks. But mostly what they're used for is for generative AI, actually. And you have things like variational autoencoders, which do things like you have special kinds like this spatial autoencoder, which, for example, you take in a chair, you compress it to the latent space, and then you rotate that chair when it comes out because it's creating a new representation in a rotated manner. So there's different kinds of architectures for this. But the reason I mention this is I'm not going to go into the setup of the autoencoder here because it'll take a little while. But ideally, what you want to do is you want to have in the multimodal case, you want to make sure that everything you compress into the latent space is correlated. And that's the important thing because modality correlation is probably the hardest thing about this whole thing. So you have a special type of architecture called a decorrelational autoencoder, which you essentially, it's two autoencoders compressed together or comprised together, which when they take an input, they compress it into their latent space, the representation is then extracted and the two modalities are correlated. So for example, if you have unaligned voice input and you have unaligned image input and you do machine learning on them using this particular type of model, and this is one in a family of models that do multimodal fusion, then those ideally, once you uncompress it from the autoencode, the DCAE space will create an aligned representation. Kind of dry stuff, but this is really important because this is the foundation of how this multimodal stuff actually works, which I think is a mystery to a lot of people, which is why I like going over it. The DCAE uses something called contrastive loss. So CLIP uses contrastive loss as well. CLIP doesn't use the DCAE, it uses something else under the hood to do the same thing, but the contrastive loss part is the important part here, which is that's a special kind of loss function which tries to find the closest representation of inputs and things that are not related to each other. It spreads those far out from each other, and so again, it's really good at identifying correlations, and that's the whole point of this model. Now the DCAE stuff is really good. It does a lot of amazing things, but it's also quite complicated in its own right. And one of the ways of balancing the complication is like playing with different loss functions. For example, you have the basic correlational loss is something like the Pearson correlation, which is like in statistics. Anyone who's familiar with that knows what that is. But then you have cross-modal matching functions, and you actually have the loss function being something that has to be learned by another machine learning model. So that's interesting. It's like a meta situation or inception kind of situation. So anyway, and then finally, around this part, I'm going to get to some more demos in a second. But what happens is in the mathematics of it is that fusion gets very complicated. It starts with very simple fusion where you're just adding things together, like 2 + 2. But then what happens is you can multiply things together and get a different type of fusion from doing that. You can then stuff things in tensors, do tensor math, tensor multiplication, and get a much more complicated representation if you have like bimodal or trimodal data. And then you get like the most complicated things, which are almost intractable problems to solve, but they actually provide the most intelligent information about a particular scenario, and that would be under something like high-order polynomial fusion. And just last on the super technical parts is like, if anyone's familiar with like low-rank adaptations, things where this is another way that you can reduce the data using low-rank fusion, because essentially this is taking parts of your fused data and intelligently selecting the parts that are important. And just a visualization on the CCA, how that works is that like if you have your, if you're trying to create a reduced space, if you are familiar with how Disney works, it's similarly in how CCA works. The visualization is more for like how to actually separate the dimensions of data. And this is more for the multimodal dimensionality. So you can have like each of these colored regions is a different dimension of like multimodal data. And so, okay, so let's see, I'm going to do a few more interesting demos. So this is Whisper. Anyone familiar with Whisper? Okay, cool. So basically how Whisper works is that the lazy brown dogs jump over the cow. So I input some voice, and then someone was talking about translation, a translation pipeline. So you can actually create a translation pipeline with Whisper, and then the output will be.
Le chien brun paresseux saute par-dessus la vache.
So this is basic, like, a language-to-language translation. I'm using, in this case, Whisper in combination with something called Tortoise NVC to do the conversion. NVC stands for neural voice coding. So again, this is what a lot of the models have much more complicated voice translation pipelines. But if you wanted to build a simple voice translation pipeline, you could use something like this setup here. Now, if anybody's familiar with generative adversarial networks, you have something called wave to lip. And you've seen all those crazy models out there which can like take someone's face and apply like sound to it and whatnot and do deep face essentially, which is something that there's quite a bit of like, there's a lot of stuff going on with deepfakes. I have a whole thing I talk about specifically with that. But this is technically a multimodal framework because it's taking lip data and combining with face data, and you're using essentially multimodal synthesis. So this is something I always show this at any presentation I do. But this is a video that I spent a lot of time putting together, but I didn't have to, but just to do the learnings of this. So
Trump is doing the most amazing things with generative AI. He's not only the greatest president, but he's also the greatest data scientist. He's making AI great again, okay? Ask Shafik Qureshi.
So basically, this is, again, this is using a lot of training data that I extracted from monologue data available online. Had to do a lot of like cleaning and pre-processing of the data, then set it up to an LSTM network and combine it with a voice synthesizer and then produce this. Deepfakes are much more advanced these days. You don't even have to do this. This is like 6 months ago that I did this. And that's not a good thing, by the way, but I'm just saying that like, this is just another application of multimodal data. You saw that the lips are moving, but those lips are controlled by the actual sound. So that's essentially an audio reactive multimodal architecture. And so eventually you get things like multimodal RAG. Okay, we're doing retrieval augmented generation using multiple modalities. I mentioned initially in the beginning, like for example, if you want to take PDF data with image data and you want to do like, we want to get some sort of output based on that, that's essentially RAG without, everyone's familiar with standard RAG, right? Text-based RAG, okay, at this point. So this is like image-based RAG or audio-based RAG. Or, as I'll go into the image bind framework in a second, much more than just that. But yeah, so again, I have a whole thing, again, that I do on just on this, but this won't be that. So if you have seen image bind before, image bind is like an amazing framework. I talk about it again at every pretty much talk that I do because I'm quite impressed by what it does, and has anyone seen this before? Okay, a few people at this point. Image bind actually takes data from several different modalities, audio, image, and video, the common ones. But then it treats things like depth data, temperature data, accelerometer data as different modalities. And what it can do is that it can essentially set up an entire RAG-based system I'll show you exactly in a second. But it also does not only zero-shot retrieval, but image bind can also do emergent retrieval as well. Again, after the demo, I'll mention what that is. But let me show you. Now, this demo comes from the site. I actually have something I'm working on specifically in, again, collab for this, for another presentation, but this comes from the ImageBind site, but this is actually, I think, speaks volumes to what ImageBind does. Okay, so we're going to talk quickly about ImageBind. So here's an example from the ImageBind site where we can combine different text, different sound and different images to get different outputs. Okay, so let's say we start with a dog barking. And then we click on this image of this beach here, and so it retrieves a dog on a beach. Okay, so if we have pouring, sound pouring, and then we click on here, the apple, automatically the system generates a faucet with apples and water pouring on the apples. Now this could be generated or this could be actually pulled. That's an interest. You can choose to do either of them actually. And then let's say we have a car engine. Click on the So essentially, you can do lots of crazy things with that framework. And so I skipped a bunch of stuff because in the interest of time, yeah, is some of the Q&A portion of this. So yeah, that's the presentation. For those interested.
Q&A. Yeah,
Okay.
some Q&A. I'm just gonna take the other mic. So who has questions? Who has questions for speaker? No questions? Intimidated?
Are you using multimodal at the New York Times in the games at all?
No, not in the games currently.
Are you using it anything else?
For explorations for certain applications, I can't talk too much about specifics. Yeah.
Any other questions? Oh.
For the first, like your paper, I guess, like was it maybe like Bayesian-based learning? Like.
Yes, yeah, basically, yeah, and yeah, you could call it Bayesian-based learning. There was no deep learning, no neural networks, nothing. It was all kind of probabilistic techniques, and then like computation based on Bayesian inference, and yeah, very old stuff.
Questions? I'll go this side.
So I'm trying to understand, why was it that you brought up Clip, and then why was it that afterwards you transitioned to Fusion-based learning? I'm not sure about the transition between those and what the connection is.
Okay, so essentially, the whole thing is under multimodal, right? So Clip is a multimodal model because it's using text and it's using images to compress things into a shared space, right? That's what's happening under the hood if you read exactly how Clip works. And it's doing essentially retrieval, or like you're doing learning, and you're doing like things like labeling and task labeling and output based on a multimodal method. So that's why I brought up just multimodality in general with Clip. To the Fusion part, I brought that up is because there's other ways to do multimodal machine learning. And when you're actually using a different, like a correlational model, which Clip is not, but many multimodal systems are, you're actually doing things like aligning them in the embedding space. So you would actually need to take, like, for example, audio and text is a straightforward one to understand. If you take like audio, it's dysynchronized from text. One way that you could actually apply multimodal fusion is that you could create a fusion pipeline. And actually I had a 12-minute video here that I did not go into because I'm running out of time, where I actually put together a fusion pipeline to do this, where I take in fusion audio data, and then I take in text data, and I take in image data, and then that is concatenated in the neural network in the fusion stage, and then it's outputted. It does classification on the categories that are output. So again, there's different ways of doing fusion. I really just kind of touched on a lot of different high level things there. Yeah.
Should we, between different models, like if there is one modality, say images, other modalities of sound, right? Temporal incoherence between the two, right? Across the training sample versus the test sample. What are the best along that you are aware of, like that you would recommend, like someone to explore, to address, like, you know?
Temporal, okay, so yeah, there's, I guess the first thing that I would say is that like, the first thing would be to understand about like things like Mel-Sepstrom, or log Mel-Sepstrom. So basically that's exactly the frequency space, when you break down sound and into like it's spectral representation. In that way you can actually find the important pieces of sound, the sound, speech in this particular case, and then you can figure out how they can align with text, because you can find a different model which picks out certain formants or fricatives, or if you're familiar with speech processing, the different examples of like different speech pieces. And then what happens is, if you want to do traditional alignment with text, you would then create some sort of like probabilistic matching filter that uses it's actually, this is under the whole thing with neural voice coding. So you would actually have to take the text and then you would like look for example, the word T that comes from the spectrum of the sound and the speech. And then you would look to find where T is output. I think overall, that's like kind of like the old way of doing it. Now these days you can essentially do these things through like things like, there's a lot of different things, like starting with essentially recurrent neural nets. You can set up a recurrent neural net to do this matching. Once you do like the extraction of the spectrum, and then you do essentially the fusion with the text mode, the text transcript of the sound. And that's where the whole correlational pipeline comes into place, because in theory, with the right correlational function, it should be able to correlate the text and the sound, and you should be able to get this alignment that is out of there. So I would look up correlational neural networks, actually. I thought I linked the paper here, but I didn't. But that's a good place to start.
One last question over here. Okay, okay, that person for a really long time, so.
Thanks. Didn't feel that long, but so first of all, I'm happy to hear you mention image bind, because nobody seems to talk about that paper. I think it's a big deal. And actually, I was like pulling it up while you were talking, because I was going to ask you about it, but you brought it up already, so that's very exciting. But I kind of want to ask you just a little bit about what your thoughts are. When Sora came out, everyone was like, it's and I think there was a lot of pushback against that. I think Fair Meta are doing incredible research, and one of the big things that Yellen Kuhn pushing back on, I think rightly so, is that these vision transformers don't have a world model, but they're doing deep work on VJEPA, IJEPA, the Joint Embedding Predictive Architecture. Tell me a little bit about what you think about the IJEPA, VJEPA work, and where world models fit into that, and where you think that whole thing is leading.
Yeah, no, great question. And to be frank, I'm not like super yet caught up to like, I definitely am aware of the controversies that's playing out specifically regarding the world model. As far as like the deep, like whether the world model exists, I agree with that. I don't think the vision transformers inherently have a world model underneath the hood. Like the physics itself is not present in there. And in my understanding, that if you want to have a world model, you would have to have a system that understands more than just matching of different like data modes and that emerge out of the machine learning. You'd actually have to have some sort of like physical systems understanding, like dynamical systems. Like it would have to be able to create equations of dynamics underneath the hood. maybe the models that have not been released yet can do that. I doubt it. I think that what appears to be a world, this is my also personal opinion, like based on what appears to be a world model, I think is just like, again, like emergent complexity that comes out of like things like the multimodal retrieval or correlation. It looks really like a world model, quote unquote, because it looks like these things have been learned. Interactions have been learned, and different motions have been learned, and so much of it can be replicated by the machine. If it eventually converges to a dynamical system of some kind in its own understanding, which I think it will be completely different than a standard dynamical system, like the way a pendulum swings or something like that. The computation will not be anything similar, though the result will be possibly similar. Then maybe that, I think, can happen. And if you want to call that a world model, sure, but it's in my belief, I'm not an expert by far in any of that. My belief, it's like a different world. Yeah, it's how I think about when you like do explainable AI and you try to like dissect what the AI is doing under the hood, and you do things like linear probing or like try to probe the different layers of the machine learning model, look at the outputs, and be like, okay, the model is doing this computation on this layer and the next layer and the next layer. At the end of the day, the model, like the example, I think I've said it like in a few different places, the 2+2 example of like, what does a machine learning model do to add 2+2 together? Well, it actually does something like some researcher found rotates a circle 168 times and added to another circle that rotated 168 times in the other direction, and therefore derived 2+2 somehow out of that. If that's a world model, that's an alien world to me. I don't know, but like that's my thoughts on it, but I'm not an expert.